In this lecture, we'll talk about heat. So in our first lecture of this chapter, we saw what is heat, right? So energy that is transferred due to temperature difference is heat, right? And heat has various units. Some of the units are calorie, joule, British thermal unit, or kilocalories, or calorie with capital C, right? So let's look at some of the conversions here. So 1 calorie, and remember there are 2 calories we were talking here. 1 calorie is starting with letter small c, and 1 calorie with capital C. If you look at this, so 1 capital C calorie is equal to 1000 small c calories. Okay, so 1 kilocalories is equal to 1 capital C calorie. Okay, and of course 1 small calorie is 4.186 joule, or 1 big capital C calorie, which is 1000 calories, will be 4186 joules. Okay, and there is a calorie, the joule is SI unit of energy, we saw that, and heat is a energy that is transferred. So heat is a form of energy, right? And British thermal unit, this is not SI unit. British thermal unit is equal to 252 small letter calories, or 1055 joule. Okay, so what is a calorie? So 1 calorie is defined as the amount of heat needed to raise the temperature of 1 gram of water from 14.5 degrees Celsius to 15.5 degrees Celsius, right? Or 1 British thermal unit is the amount of heat required to raise the temperature of 1 pound, which is weight, here 1 gram is mass, of water from 63.0 degree Fahrenheit to 64 degree Fahrenheit. All right. So with this background, let's work on the quantity of heat. Let's say Q is denoted by quantity of heat, and of course the unit will be joule. So quantity of heat. So if you have to use your experience, then if you want to raise the temperature of certain amount of mass, let's say 1 kilogram of water, by some temperature, let's say 10 degrees Celsius, you need certain amount of heat, right? And if you double the mass, say let's say 20 kilogram now, and then the amount of heat you need to raise the same temperature, it would be more, right? So we can conclude that Q, a quantity of heat required to raise the temperature by some amount delta T, is proportional to mass of the material, right? Water. How more is the water, more quantity of heat you need, even if you are raising by the same amount of temperature. Same way, we can argue the quantity of heat required is also proportional to delta T. Delta T is change in temperature. So for example, if your mass of the water is 1 kilogram and you want to raise by 10 degrees Celsius, will be less than if you have 1 kilogram of water but you want to raise the temperature by 20 degrees Celsius. Probably you will need twice that quantity of heat, right? Because your mass, because your delta T has doubled, right? So if I combine these two, the Q is proportional to mass, Q is proportional to delta T. If I combine the two, then we get an expression which is Q, the quantity of required, is equal to some constant of proportionality, and I denote it by small letter c, then mass of the material or substance and how much temperature you want to raise, right? So Q is equal to Cm delta T. This is first relationship, which gives to raise the temperature by delta T. And you say, what is C? C, and this is small letter c, is equal to specific, is called specific heat of the material, right? And I've been saying water, water. So if this is water, then specific heat of water. And in this lecture, in this chapter, we will use, in most of my material will be, or a lot of time our material will be water. So specific heat of water is 4190. And what's the SI unit? Then Q is quantity of heat. Heat is in energy, so joule. M is mass, kilogram. Delta T is degree Celsius or Kelvin. So we can say joule per kilogram per degree Celsius, right? And this is for, so specific heat of water is 4190. Okay, so this quantity we'll use very often. Sometimes it is convenient to describe a quantity of substance in terms of the number of moles, N, rather than the mass M of the material just described earlier. So if N is the number of moles, right, N is the number of moles, then, and M, capital M, is the molecular weight, is a chemistry term. It's not really weight, it's a mass. So molecular mass or molar mass is equal to molecular weight is defined as mass per mole, right? So M is the molecular weight of that material, and there are n number of moles, then the mass of that substance will be given as N times M, right? And from the earlier relationship for heat required to raise the temperature of mass M kilogram by some temperature delta T, let's say degree Celsius, that's the relationship we saw. And now we can replace the mass in kilogram in terms of the molar mass and molecular weight, and this is small c delta T. Then this is equal to N, the number of moles, and I see capital C delta T, right? So this is Q, heat required to raise the temperature of n moles, n number of moles, by certain temperature delta T. And here the capital C is called molar heat capacity. Molar heat capacity, or also you can say, or molar, because it's related to moles, molar specific heat, all right? And for water, M, the molar mass or molecular weight, is 0.0180 kilogram per mole, right? That's what per mole, that's what we mean mass per mole. Then C, the molar heat capacity or molar specific C, will be given as remember C is M times C, so that will be 0.0180 kilogram per mole. This is my M. This is my M, and the specific heat is, if you remember the earlier one, it was a 4190 joule per kilogram per degree Celsius. Right? Then we can say that C is, if you multiply the two numbers, which will be 75.4 joule per kilogram per degree Celsius, or joule per kilogram per Kelvin. Right? And this value 75.4 is the molar heat capacity of water. So I can put the suffix here, water. So water. So C, water, molar heat capacity or molar specific heat of water is 75.4 joule per kilogram. No, this is kilogram, and kilogram cancels out, so it's not kilogram, it's per joule per mole per degree Celsius. So so sea water, molar heat capacity of water is 75.4 joule per mole per degree Celsius, or joule per mole per Kelvin. All right, great.